What's up, guys? In this video I'm going to show you a really cool circuit I just whipped up that allows you to control anything you want by whistling. So just like that. So it's pretty cool stuff. I'm all the way over here. Over there I have the microphone circuit set up on a breadboard and it's hooked up to that light. So let's take a closer look and see what's really going on there. Okay, so here's the circuit, and to be honest with you, this is very rough. This is just done with components I had laying around in a very quick and dirty way. I just whipped this up really quick to see if I could do it. And I was actually inspired to do this based on a project that came across online, a really cool project called Whistled. He did it a completely different way than what I'm going to show you here, but he actually used FFT fast Fourier transform to conduct a frequency analysis on the incoming signal and blah blah blah. It's really cool. I'll put a link in the description below to that. But what we have here is more of an analog approach to detecting whistles. This is the microphone over here. That feeds into a preamplifier circuit, then that goes through a bandpass filter, and then we amplify the crap out of the signal. Then the output there feeds into a comparator where we can adjust, the sensitivity of the whole thing. And then the output of the comparator feeds into an interrupt pin on the Arduino here. This is a standalone Arduino, so this is an ATmega 328 with all the crystals and caps and everything you need to program an Arduino on a breadboard. So this is the USB to serial converter over here. And that's it. So this is the same thing, by the way. This standalone Arduino is just your Arduino Uno or whatever. So and you probably can see that we have these flashing LEDs here as I'm talking. And the way I wanted to do this was not to detect single tones. Like I wanted to turn things on and off by a sweep up in the whistle, like a kind of thing like that. So it needs two frequencies to detect within consecutively and close to each other, like within 50 milliseconds. So that's exactly what we have here. And in fact, we have two trim pots here that you can adjust to detect or to adjust to those two different frequencies. So you can see the yellow LED here is for the lower frequency, and then the purple LED is for the higher frequency. So if I whistle here, I'll go to the lower one. And then the higher frequency one is, so we're detecting both of those. And in order to turn stuff on, it needs to hear the yellow, the lower frequency, the yellow LED, then the purple LED. So it's got to go. So you see, the first time it didn't do it, because that's the other thing I wanted to do. I wanted it to hear it twice within 1 second. Okay, and I don't know, and we'll go through the code to it here in a little bit, but. And by the way, the blue LED there in the middle is telling us whether or not the appliance is on or off. And this is a relay here, and you probably can't hear that clicking, but basically the blue LED corresponds to the status of that relay. So, and you can see that's how it works. So it's really cool. And by the way, if you're going to build this circuit, you almost need to have an oscilloscope. Okay, so if you don't have an oscilloscope, it's going to be really hard to tune the entire circuit to work. You might be able to get it done, but it's going to be rough. So anyway, let's go to the whiteboard and take a closer look at some of the theory behind what's going on here. All right, so the first part of the circuit is the microphone input and biasing circuit. So when you buy the microphone, this is just a standard electric microphone. It's got two wires on it, one's the positive wire, the other one's the negative. Tie the negative right to ground, and then the positive wire goes through this biasing circuit here. So what we have here is a 10K ohm resistor connected to 5 volts, and then this is a potentiometer, but we're only using 2 pins off of the potentiometer, so we're actually using it as a rheostat. So you can kind of see what I've got going on there. But this is just so you can fine tune the output here, the signal here. So I use the 10K ohm potentiometer for that, and then the output here is connected through a 10 microfarad capacitor, and then this is the output audio signal, okay? And then this feeds into the preamplifier circuit, which I'll show you next. And by the way, it took me a long time to actually figure out which values to use for this. So if you look online, you might see some people are using 1Ks here instead of 10Ks. And this is part of the reason why you want to use this. You need a scope for this kind of thing so that you can hook a scope up here and fine tune this until you get it just right. Okay, so let's look at the preamplifier circuit now. Okay, up next is the preamplifier out after the microphone. Because the microphone signal is going to be really weak, and it's going to be centered around 0 volts. So we feed it into the LM386 here, which is specifically designed for audio applications. And in fact, if you don't build this circuit up, it's probably good to have a few LM386s on hand because it is a cool chip, and you can interface to speakers or headphones or whatever you want with a chip like this. So right across pins 1 and 8, we have a 1 microfarad capacitor, which gives it a big gain or a big boost to the gain. Pin 2 is grounded, pin 3 is your microphone input, pin 4 is grounded, pin 5 is the output of this thing, pin 6 ties up to 5 volts, 7 nothing, and then of course 1 to 8 is the 1 microfarad cap. Few notes about this. Very important to have big bypass caps hooked up. So right across 5 volts and ground, right at the pins of this chip, you want to have, your 0.1 microfarad cap. You want to have a 1 microfarad cap, 10 microfarad cap. Just line them all up, and this thing will work pretty good for you. The output here is going to be, let's see, hopefully you can see that. Yep. The output here is going to be, so if your VCC is 5 volts here, it's going to be centered around 2.5. So here it was centered around 0 volts, the swing up and down. Now that's going to take that signal, boost it way up, and it's going to be around 2.5 out. The output there then heads over to the filter part of the circuit. So let's take a look at that. Okay, so here's the filter stage now. And one thing I forgot to mention before, part of the LM386 circuit is to connect the output directly to ground through 2.1 microfarad caps, okay, to give you 0.05 microfarads there through a 10 ohm resistor to ground, okay. Then it feeds into the bandpass filter here, which is nothing more than 2 RC circuits. So the first one here, this is your low pass filter right here. And so we have two 10 ohms in parallel here to give you 5 ohms with a 10 microfarad cap to ground. So your cutoff frequency is going to be 1 over 2 pi times 5 times 10 microfarads. And it gives you a cutoff frequency at about 3 kilohertz. So this will pass everything under 3 kilohertz. The next up is the high pass filter. So right at the output of that feeds into a high pass. And again, the frequency or the formula for that would be, well, in this case, it's two 10s in parallel with a 10 to ground. So that's 5 there plus 10 is 15. So that cutoff frequency calculation is 1 over 2 pi times 15 times 10 microfarad. And that's cutoff frequency about 1 kilohertz. So this will pass, this whole circuit here will pass anything between 3 and 1 kilohertz. And it's not really perfect. I mean, passive filters are just awful for this sort of thing, but it does a pretty decent job of blocking things out. And sort of as I whistle, as I go through this by going, if you look at the output here, you can see it sort of like do that as I get close to right in between here. So it's kind of cool, and it does work for what I'm trying to do here. So let me just show you what that kind of looks like. And by the way, I have a video on RC circuits too that breaks down that formula and exactly how it's calculated. So that first one, the low pass, looks something like that, where this is supposed to be 3 kilohertz. And then the other side then is coming this way, where this is supposed to be like 1 kilohertz. So my gain, everything that comes through in this frequency should come right through at 5 volts. But of course it doesn't. There's a lot of drop in there and it's not perfect. And a lot gets through, even like as I'm talking now. Obviously I'm not talking in this range, but there's a lot of high frequency content in my voice, so you do get a lot of stuff through there. So anyway, the output of that then feeds into another amplifier circuit. So let's talk about that now. Okay, so I just took a little break, so hopefully I remember kind of where I left off. But I believe we just left the high pass filter, so the overall bandpass filter. We just left the high pass filter, and now we're entering into the big giant gain, the boost on the signal. And for that we use a non-inverting op-amp circuit. I use the LMC642 dual op-amp chip, which is pretty good, but I don't know if it's the best thing to use for this type of application. But one thing I want to talk about, though, before we talk about this, is after the high-pass filter, the signal is really weak, but it's biased around 0 volts here, meaning that we have positive voltage and minus or negative voltage coming into it, and it would enter in right here on this pin. Well, the negative voltage is kind of useless to us in this case because I'm not going to bump it back up to center it around 2.5 volts. I don't really care. And since this is a single rail op-amp, meaning I only have 5 volts applied to it, 5 volts in ground. I don't have 5 volts and negative 5 volts applied to it. So it's single rail, so I really don't want this negative voltage coming into it. When we're normally using the circuit or talking right now, there's not a huge signal here, so it's not really going to damage it. But if I clap my hands really loud, close to the microphone, you might get a huge spike, negative spike, and I don't want that damaging the op-amp. So a quick and dirty kind of way to fix that, or to clip all of the negative voltage there, is to put in a clamping diode right here to ground. So what happens is if this voltage ever gets smaller than negative 0.7 volts, this diode will become forward biased and clamp that signal to 0 volts. So that's what I put in the circuit just to kind of protect the input. I doubt it would ever actually harm this, but probably a good idea to put in there. And this is just any general purpose small signal diode you can find. There's nothing special about it. Okay, so that's enough about that. Now we're into the non-inverting op-amp. And this configuration is the non-inverting op-amp circuit, and probably a good idea just to go through this and how it works. So this is VI right here coming in, and the op-amp will do anything it can to maintain the voltage between these two input pins. So it will do anything to VO to make sure they're both the same, okay? And obviously we want negative feedback, not positive feedback, so our input signal is to the positive input, and our feedback is on the minus input there. And if we figure this out, you can see that VO is just setting up a voltage divider for VI. So if you just kind of look at that, that means that you have VO divided by the current through there. There's no current going up through here at all. R1, or in an ideal op-amp there is none. R1 plus R2 times R2 gives us VI. Okay, and the gain is you represent the gain by VO over VI. So if we kind of rearrange all of this, for now we'll put VI over VO. So divide both sides by VO. That gets rid of that, and you're left with this. And then since we want it to be represented VO over VI, we kind of flip everything around. Let me just do that real quick here. So that was, and hopefully I can remember how it was, over R2 is equal to VO over VI. Hopefully you can see that on the camera. Yeah, I think so. And then if you simplify this, that leaves you with, I could break this fraction up, and that leaves you with R1 over R2 plus 1. And that is the gain of this circuit. Okay, so what I did was I set this R1 up equal to 100K. And then R2, I kind of played around with R2 a little bit. So right now, the way I have it set up, I have R2 set up to be 100 ohms. Let me get rid of that. So the gain of that is R, or did I put that right? I think I did. So the gain of this circuit is 100K divided by 100 ohms, which is 1,000 plus 1. But let's just forget about the plus 1 for now. So that's a gain of 1,000. That's a huge gain. And that's sort of what I have it set up for. In fact, I actually, you can play around with this. I put a pod in there to play with it, and I gave it like a 1K in there too. And that seemed to work pretty good too. So yeah, that's the whole circuit. And basically the output we get, since we're clipping the negative section, so we've got some input signal that's coming in, and it's it's around 0, and then our output is now kind of like, looks like that. So if this 0 volts, and then this is 5 volts. Okay, so that's the output of that circuit, and let's move on. Now what we do with this is we feed that into a comparator, and I'll explain why that is here in a sec as well. Okay, so on the this is the LMC642 is a dual pack, so it's got 2 op-amps in the same package. So the other op-amp in the pack I'm using for the comparator. So right here on pin 5 is the output then of our amplifier, and it jumps right over to pin 5, and it's compared with the signal coming in on pin 6. Okay, and the way a comparator works is anytime the voltage here is greater than the voltage here, the output will go to the rail, which is plus 5 volts. It'll go to the positive rail. If the voltage on pin 6, or the negative input, is higher than the voltage on pin 5, the positive input, the output will go to the negative rail. And in this case, we don't have a negative rail. It's just 0 volts. Okay, and basically what we have on pin 6 is just a potentiometer. Okay, so the 2 outer pins on the pot are connected to plus 5 volts and ground, and then the wiper is connected right to pin 6. So that allows us to adjust this. And basically the reason I wanted this is because the output here feeds right to the interrupt input pin on the Arduino. So, and we don't want like kind of crappy like analog signals, right? We want big inputs, like slammed to 5 volts. So let me show you kind of what this is doing. So I don't know if this is going to look good, but let's say we set the wiper to like, let's set the wiper, like 1 volt or so. So the wiper voltage is right here. So if I've got all this crap going on like this on pin 5, the output will just stay low the whole time. But if we come through here and we've got something like that, we start whistling and we start seeing something like this, and the amplitude is kind of like waving a little bit, well, we'll get, anytime this is greater than the wiper, we'll get a big slam square wave on the signal like that. So the output of this thing is a square wave representation of the input frequency, and this allows us to adjust the threshold. So if you got a lot of background noise going on, and you've got just a ton of crap going on, well, this allows you to adjust it so it's only listening for the whistles above the ambient background noise, and then the output is that nice square wave. And I'm gonna pull this up on the breadboard and the scope, and I'll show you kind of how it all works. Okay, and that is pretty much it. This same wiper circuit here, I also have two potentiometers hooked up to the 2 analog inputs the same way. So I'm not going to go over what that is, and I obviously don't have to go over what LEDs, how to hook up LEDs or the relay or anything like that. I've got plenty of videos on that. So anyway, let's take a look over at the breadboard and see what's going on. Okay, so now that we've seen or broken the circuit down, I think we can work our way through the circuit and show you the output of each one of those function blocks and show you kind of what it looks like on the scope. So right here, this is showing you the this is the output of the microphone. So, and I've got it set up for 1 volt per division. So even that, you can't see anything on the scope. So let's break it way down. So now we're at 20 millivolts per division. Now you can start seeing it wake up a little bit. So it's still, you can see that it's really a tiny signal on the scope screen. So then it goes through the LM386, and let's look at the output of that. Okay, so now we can go to 1 volt per division, and you can see that if we be quiet, it's centered around 2.5 volts. And as I talk, you can see it's giving you everything. So now it's done a great job by amplifying it up. Just gonna change the time divisions there. So now, okay, so you can see the output there. Let's look at the output of the low pass filter. That's right here. Probably not going to be able to tell much from that. A little bit, not much. All right, let's look at the output of the high pass filter. If I can get to it. There we go. Okay, it's right here. So you can see what's kind of cool here is that I've clipped. So this is the 0 volt. And you can see if I give it something, you can see it start to kind of clip there. Maybe if I give it something big there, you can sort of see it sort of the clamping diode there, clamping the bottom of it. Okay, so let me see if I could show you sort of how the high and low pass filter are working. So I'm going to sort of try to whistle up and around 1 to 3K. So, you know, come in and out of that pass zone. Okay, it's kind of hard to tell. Okay, so you can kind of see it a little bit. Again, this is just one high pass filter, one low pass, so it's, you know, you're not really getting a great rise or fall off there, you know. So it's, if I added another stage to it, it would drop off a lot sharper than it is now. All right, let's look at the output of the amplifier, that big boost. Okay, this should be interesting. Okay, so it's huge. Okay, here we go. Probably don't have to be that high. So you can see it's like amplifying everything. Am I looking at the right spot? Yeah, I am. So it's like every time I talk, you can see it. It's smashing right to the rails. It's hardly analog at all. In fact, I might just real quick, I'm going to swap that 100 ohm out for a 1K. Give it a little bit better gain on it. So yeah, see now you can see, like, as I talk, I almost have to be like really close to it. So that's still kind of in the mud. Okay, so anyway, now let's look at the output of the comparator, and this feeds right into the microcontroller. And you can see, so I already switched it to the 1K, so I don't know how well this is going to be. So I'm going to bring down the level of the comparator, that potentiometer, and oops. So you can see that, see, it just switched. I just brought it above the noise floor. So if I bring it down a little bit, okay. Okay, so I'm right now, I'm just, the level is right above the ambient noise. And you can see as I talk, I'm tripping it. So, and now it's just purely square waves. So it's going to slam all the way up. The LMC642 isn't the greatest comparator to use. You know, you'd probably want to use a Schmidt trigger type open collector output comparator op-amp. You know, an op-amp that's actually designed and made for comparators to be used as a comparator. So now you can see, like, look how perfect the waveform looks when I whistle. It has perfect frequency content, and it's a nice square wave. And now you can easily see how it's clipping the higher frequencies off in the lower frequencies. So, you know, now it sort of brings the whole circuit together, and now it sort of makes sense why we did it, why we actually use all these different functions. And you can see it. So it works. So when I'm really low, it doesn't even hear me. And when I'm high, it kind of hears me a little bit, but you can see it's like right in that perfect 1 to 3 kilohertz is where it really likes it. So anyway, that is the whole circuit. I'm trying to think if I forgot anything. And sorry, I mean, this is probably one of my most rushed tutorials, and I can't even think straight today for some reason. So I just kind of whipped this up. I'm rushing through this just so I can get this out, because if I don't make this tutorial, like I said before, I probably wouldn't ever make it. So hopefully you guys like this. Now I'm going to show you the code, and the code, if you think this circuit is ugly, the code is hideous. All the variable names, everything is just, it's bad looking. So anyway, let's jump over to the code and see if even I can figure out what the heck I did here. Okay, so here's the code, and you know, it's really bad looking, but I do want to at least just get this out there, so if anybody actually wants to try to build this or try to understand what's going on here, it's at least available. You know, this is a pretty cool project, so I might actually revisit this, clean up the code, clean up the circuit, maybe put it on a proto board, something like that. So maybe I'll make a follow-up video. But anyway, let's just work through this line by line and try to make sense of it all. All right, so we've got a few variable setups here. Then in the setup, I was using the serial port for a while to print out the frequencies at which, you know, it was measuring. Here's the interrupt pin, so that's digital pin 2 on the Arduino. It's interrupt 0. It calls subroutine heard, so it heard, you know, something, and it trips on the rising edge. Okay, and then we have a bunch of LED outputs. Pin 12 I'm using as the digital pin 12 I'm using as the relay output, so it drives a transistor to pull a relay open and closed. All right, and in the loop, we have the 2 trip frequency analog reads. So it's doing a map. So it does an analog read from pins 0 and 1, analog pins 0 and 1, and that data can range from 0 to 1023, but I want to map it from 2 to 2000, and that's exactly what this function does. It's kind of handy. So it's making, if it read in a 0, that equals 2. If it read in a 1023, it presents it as 2000. Okay, so that's kind of how that works, and it maps it, and it gives you a nice linear, adjusts the linear curve, I guess. Okay, we do that for trip frequency 1, 2, and then we have this thing here called if ding 3 is equal to 2, and basically this is what turns the relay on or off. So in order to turn your relay on and off, ding 3 must be equal to 2. So, well, obviously I don't do that here in the loop, that's handled in the interrupt. So, but let's just say if ding 3 equaled to 2, we would detach the interrupt. Okay, we would digital write pin 12, the opposite of what 12 is right now. So it just flips it over, and then it sets all these variables to 0. We'll talk about that more. Then we do a little for loop to 20, and this is digital pin 10, and it's doing the same thing, just flipping it. And this is just an LED. That's that blue LED. So flash the LED 20 times, actually 10 times, since it flips it opposite, every time. And then finally write digital pin 10 what digital pin 12 currently is at. Okay, and that's the whole thing. And then reattach the interrupt. So this is just the function to turn stuff on and off. And all right, let's keep going. So that's all that's in the loop. Everything else is here in this void heard. And this is called when that interrupt pin goes from 0 volts to 5 volts. And we use a lot of the micros and the millis function a lot in this. So the first thing it does is it calls our period is equal to micros minus time start, which means nothing right now, but it will the next time it's called. So ignore that for now. Pretend it just put garbage in there. Time start is equal to micros. Okay, so it just suddenly this got called, and it puts in some value. And micros is just a number that's being counted in microseconds since the Arduino started running. So it starts counting, timestamps it. Then the next time this is called, then we take the period. We measure the time between the rising edges, and that would give us a way to measure frequency. Okay, so that's exactly what we do here. And we get some value for period the next time it's called. Since now micros has grown a little bit or counted, a few microseconds or whatever. So we could take that value minus the one it was at, and we get the period. Okay. And then a whole bunch of crap commented out. I don't know what I was doing there, but I'll leave it in there just in case you want to see kind of what I was doing here. Okay, so now we have a period, and we have a trip frequency for trip frequency 1. So what it does here is it checks it to see if it's in range of where we were. So if period is less than the trip frequency plus 100 and it's greater than the trip frequency minus 100, so it's checking it within a tolerance of plus and minus 100 microseconds. Okay, and if it is, go ahead and write digital pin 11 high, which is the yellow LED. So as I'm talking here, when you see that yellow LED flicker up, that's because this is getting called. And then we have these dings set up. See, when I was first writing this code, I was just making up variable names, and that's what I chose. I don't know why. So if ding is less than 2, forget about the less than 2 for now. But let's just say it is, because it is right now. We're going into the code for the first time. We have this variable in between time tones is equal to millis. And millis is like micros, but it counts in milliseconds. And it keeps going. Okay, so anyway, it keeps going. We're in here, ding plus plus. So we get an increment on ding. So that means that we've counted one successful period. So we've got one ding. Okay. If we don't get a successful, so if this is called, if this thing is heard is called, but we don't see anything here, then go ahead and what we have here is, well, obviously write the yellow LED low. But if ding is less than 3, so if it hasn't counted up to 3 yet, then make ding equal to 0. In fact, this should probably be 2. So I'm kind of finding bugs as I go through this. So the whole idea is having 2 tones. So this is the first tone. So if you keep going, at that lower tone, eventually ding is going to get higher than 2, and we don't care about it anymore. Then we're concerned about the higher tone. Okay, I guess that's what I'll call them. So low tone, high tone. So eventually it'll get past this, and then it won't reset itself back to 0. So we don't care. All right, so that's the whole thing inside of the first tone. Then the second tone, the higher frequency one, is trip frequency 2 plus 100 and minus 100. So it's the same thing as up here, but we have a different frequency in there. And this is kind of the same thing, but in here what we did is I did something kind of goofy here. And this might not make sense, but basically, if ding is greater than 2, which it is, right? Because we'll go in here. We'll say that we successfully got down. If it's greater than 2, and millis minus the in-between time tones is greater than 10, and the millis minus in-between tones is less than, there's a 500 over there, so it's 500 milliseconds, then ding 2 plus plus. So what we're doing here is right here. See, remember this is where we were taking the first in-between tone. So if I went, it would have counted ding up. Eventually ding would have become 3, and as soon as that happened, we're taking a snapshot in time of what millis is in between time tones, so that you catch the sweep up. So basically what I'm trying to do here is I don't want it to go, I want it to be fast, like a kind of thing. I almost can't whistle anymore. So that's what's going on here. So it's got to be greater than 10 milliseconds, but less than 500 milliseconds. So once you make a successful low tone, you need to make the high tone within 10 to 500 milliseconds. And that's all that's happening here, okay? So as soon as I go, this hits 3, boom, takes a snapshot. Now I have that, and I can go millis minus the old, and I can figure out where I am now, okay? Kind of a complicated way of doing this. And again, I know this, you can bail out anytime, trust me. You won't hurt my feelings. This code is ugly, it's bad, there's no comments. In fact, this isn't even how I would do it if I actually spent time on this. I think I would completely do this differently. So anyway, so let's say now we went, and you've successfully ding 2 here. You've got a few counts on ding 2. So you actually did successfully go a low tone to a high tone. So now ding 2, if ding 2 is greater than 2, then reset ding 2 and ding. So it's a successful ramp up. Then we go into this, if ding 3. So I stopped here. When I first did this, I would have stopped here, but then I wanted it to go kind of thing, you know? So you needed 2, and that's what ding 3 comes in. So now we have in-between time of whistles. So this is in between the 2 tones, the low and high tone. This is the time in between the 2 kind of thing, okay? So we grab a screenshot, or not a screenshot, snapshot of that time at which you made the first one, and then we set ding 3 to 1. So the next time through here, this would not be called. So we did that, and then it basically jumps out of all this crap. So pretend it jumped out. Now we do a second successful. Now ding 3 is equal to 1, so this wouldn't be called. Ding 3 is equal to 1, and let's say that the time, now we're doing the same thing we did between tones. If millis minus the in-between time whistle is greater than 50 and less than 2 seconds, so there's a less than 2,000 out there, then we can go and make ding 3 equal to 2 and then reset everybody else. Okay, so now you see where ding 3 is equal to 2. So if we jump back up into the void loop up here, you'll see ding 3 equal to 2, and then it resets everybody. Okay, so it's I know it's obnoxious. So ding 3 is now equal to 2. Everybody's reset. But let's say we got one successful one, but this timed out. You're not less than 2,000 milliseconds. Then it'll chill out and nothing happens. And if it's ever greater than 3,000 milliseconds, then it will reset ding 3 to 0. So like if you just got one successful one, like then it times out and nothing happens. The reason for the greater than 50 here on both cases, this is greater than 10, this is greater than 50, is just because like if you're in like a sweet spot or there's like a lot of cheering in the background on TV or whatever, I don't want it to just trip, you know, with a constant kind of wobbly tone. I want some silence in between them. So I want like a, even if it's fast. So even if you can go, I mean, this could even be stretched out a lot too. But anyway, that's kind of what I was thinking there. All right, so let's say now, this is all for, this is only if you came in and your ding 2, or no, this is if you had a successful ding to begin with. So otherwise, you could still call this whole function even though you don't have a successful low tone yet. And then that's what's outside here. So else ding 2 is equal to 0 and digital write 9 low. So that's the purple LED. So it's still going high and low even if you don't have a successful low tone first before making a high tone. And that's good to have so that I can tune the two frequencies without going. I can just go and wait for that LED to come on perfectly, then do the high tone, wait for it to come on perfectly. And anyway, that's the code. Man, it is bad. Even as I go through this, I'm almost embarrassed to put this up online, but it's a really cool kind of idea. It's really, really finicky. I can almost guarantee you that if you try to build this circuit and follow my code, I'll promise you that it won't work. You have to fine tune it. This is analog design. The fact that it's built on a breadboard, I mean, the inter-pin capacitances are affecting the way this circuit behaves. Okay, so this is totally different than your standard Arduino kind of basic circuits. This is a full-blown out analog design, so every little thing is going to affect how it responds. Okay, so in fact, get this. I have a little like USB kind of charger that I plug into the wall. If the breadboard is powered off of one of those versus the USB port on my computer, it completely acts differently. Even the tuning is different. So there's like noise getting onto the 5 volts, and that noise alone is enough to screw up everything on the circuit. I mean, it still works, but I have to go in there and fine tune it. So anyway, that is that's kind of one of the challenges of this whole thing. So if you're still with me, thanks for watching. It's been kind of a long video, I know, and hopefully I'll make a follow-up someday with a more polished version of this whole thing. But I thought it was just a really cool project I wanted to tell you about. So thanks for watching.